as you get to each functional group, which you really don't hit most of them until organic 2. So if you're not taking organic 2, it really will be a memorization type thing for you. But they'll be talked about more if you do hang on a moment to get to those chapters. And that's really it for chapter 2. Chapter 2 is pretty short. Chapter 3, there's 3 main topics. There's nomenclature, which is a fancy term for naming. I'm going to spend probably a solid hour on that tonight. We're going to do what's referred to as naming alkanes, and there are multiple other functional groups out there, but their naming systems are all based off the alkene naming system. So the alkanes are by far the most important naming system for you to get down. So I spend a lot more time on naming at this point than I will later on in the semester. When we get to alkenes, I'll mention a little bit about it. Alkynes, I'll mention a little bit about it. Alcohols, I'll mention a little bit about it, but most of it's going to be done with the alkanes. So it's going to be pretty in-depth as far as what I'm going to go through. But once you get those rules, those are pretty much the rules. So that's probably half of chapter 3. As far as the rest of chapter 3, it's like 25 and 25% for the remaining 2 topics. So it's what's referred to as Newman projections and Sherritt confirmations. So I'm going to try to get through up to the Newman projections tonight, and then hold the Sherritt confirmations over until next week. But as far as asking the bases, that's going to be the first thing to go over for chapter 2. And I know I jumped ahead a couple slides where I left off. I stopped here with the branching of the alkanes. This slide, the hydrogen bonding, and this slide, the hydrogen bonding, and this slide, the boiling points and molecular forces. You can cross those out. I'm not doing anything with those 3 slides. So, and that brings me to the acid base part. So as far as acid bases, when you took Gen Chem 2, you should have spent a good amount of time on this. You should have done pH calculations, Ka calculations, ionization constants, buffers, titrations, strong versus strong, strong versus weak. There's a whole lot you did with it. We're not doing any math as far as the acid bases go in this course. It's more just theoretical structural basis, identifying what's stronger, what's weaker, just looking at the structure of what you're dealing with. What makes acid bases difficult is there's 3 types of acid bases that you cover as you go through chemistry. When you took general chemistry, the Bronson-Lowry theory is by far the most important. As far as organic, the Lewis is by far the most important. The biggest issue with that is that most professors don't really go over the Lewis acid bases other than to say this is what the definition of Lewis acid, this is the general way to recognize it, this is the definition of Lewis base, this is the general way to recognize it. So I'm probably going to do the same thing tonight as far as just going over the definition and how you recognize it, and then as we get into the later chapters, I'm going to show you how it applies as an acid base. But as far as these 3 definitions, Arrhenius, I don't have any slides on that one because it's not going to be used. It's a very limited definition. First off, it only applies to liquids, and there's plenty of acids and bases out there that are not just liquid state. You have solid acid-base reactions, you have liquid gas acid-base reactions. The other reason why it's not that useful is that it says that all acids produce H+, all bases produce OH-, and there's going to be multiple acid-base reactions in organic that don't produce OH- or don't produce H+. So as far as that definition, you're not going to see that one showing up. I don't know if they mention in the book, but if they do, don't pay attention to it. Bronson-Lowry, I'm going to mention a little bit on it because it does have some applications in terms of organic. From a reaction standpoint and the mechanistic standpoint, Lewis by far is the majority of what you're working on. But just for basics on identifying what is the most acidic, what is the most basic area within a molecule, that's really where Bronson comes in. So for Bronson-Lowry acid bases, as far as the definitions for each of these, in terms of a Bronsted, and I'm going to put these up now just so I can kind of get Lewis out of the way. As far as the Bronson-Lowry acid, the definition of a Bronson-Lowry acid is that it's something that loses, or another way of saying that is it donates a proton. And for all intents and purposes, the proton is represented by the hydronium atom, which is just an H+. A Bronson-Lowry base is something that accepts or gains a proton. So as far as the Lewis definition, after all these years of me doing this, I still don't off the top of my head memorize the Lewis definition. I know the Bronson definition, and I know the Lewis is the exact opposite of it. So Lewis structures, everything he dealt with, that ever involved the term Lewis, dealt with electrons. Lewis structures, you're positioning electrons within the structure, showing how the bonds are made, what's along there. So Lewis is dealing with electrons, whereas Bronsted-Lowry deals with protons, or H pluses. Wherever a Bronsted-Lowry would gain, this is going to lose. Wherever this would lose, this is going to gain. Lewis is literally the exact opposite of the Bronsted theory. So if you know the Bronsted theory, if a Bronsted-Lowry acid is going to lose a proton, then a Lewis acid is going to end up gaining an electron. And likewise, if a Bronsted-Lowry base is something that gains a proton, then a Lewis base is going to be something that loses an electron. Everything about the definition is the exact opposite. Where you lose a gain, where you have a proton, you have an electron. So those are the general definition of each. I'm going to mention the Lewis acid and Lewis bases a little bit more towards the end of this chapter. In this chapter, they refer to them as Lewis acids and Lewis bases. Going forward, they're not. They just kind of the term Lewis acid and Lewis base later in the book just kind of drops off the map, and we don't really mention anything about it. There are other names. There's another name for what a Lewis acid is, and there's another name for what a Lewis base is that you're going to see the book using throughout the rest of the semester. And those are the terms that you're really going to want to get familiarized with, which is why I don't want to harp too much tonight on what a Lewis acid and Lewis base is, because I'm not going to be referring to them as Lewis acid and Lewis bases going forward once we get out of this chapter. But a Lewis acid is something that gains an electron. So another name for that is an electrophile. Electron, file, loving, electron, loving, you're gaining electrons. Another name for a Lewis base, which is something that's going to lose electrons, is a nucleophile. So in this chapter, they're going to briefly mention what a Lewis acid is, what a Lewis base is. And again, once you get out of this chapter, they're going to be talking about Lewis acids and Lewis bases throughout the entire book. They're just not going to be calling them Lewis acids and Lewis bases as we go forward. So when you get out of this chapter, a Lewis acid is an electrophile, a Lewis base is a nucleophile. And the reason why I don't want to harp too much on this is because this is how I'm going to be referring to them and discussing them. So when we get to electrophiles, when we get to nucleophiles, I'm going to make clear what an electrophile is, what a nucleophile is. So I'm not going to drag too much on what the Lewis definition is, since I'm just going to be changing the name later. So as far as this chapter, really Bronsted is what this is going to be covering. So for Bronsted, it's something that can donate a proton. Bronsted-Lowry acid is something that donates or loses a proton. Base is something that can accept a proton, which is going to be just an H plus. If you were looking at a reaction, say you're looking at the third reaction down. And the reason why I'm looking at the third reaction down is just because that's dealing with organic acids, and that's more how you're going to see these presented as in your organic chemistry class. But if you didn't have the term acid and base labeled there, you'll be expected to identify what the acid is in a reaction and what the base is in a reaction. So as far as a Bronsted-Lowry acid, an acid is something that loses an H. So what started out with an H and ended up without the H. So looking at from left to right, that HC double bond O, OH at the left, that lost an H, because on the left side it had an H, on the right side it didn't. Since that lost an H, that's classified as an acid. The CH3O negative on the other side ends up being a CH3OH. It gained that extra hydrogen. So to gain the hydrogen, it's going to be your base. Then there's a term conjugate. A conjugate is considered it's the conjugate opposite. Whatever the acid turns into is the conjugate base, and whatever the base turns into is the conjugate acid. So if you've got an acid and you've got a base, whatever the acid turns into is now your conjugate base. And whatever the base turns into is now your conjugate acid. So the acid that was on the left, whatever it turned into on the right, that's the third piece in, that's what the acid turns into, that's your conjugate base, and then whatever your base turns into is your conjugate acid. There's a part of that you're going to have to be familiar with. So you need to be able to look at a reaction and just generally in front of you, look at a reaction, identify what was the acid, what was the base, what did the acid turn into, that was a conjugate base, what did the base turn into, that's conjugate acid. So you should be able to look at a reaction and identify those four components of the reaction. As far as acid strength, when you're dealing with weak acids, you have strong acids and you weak acids. Definition of a strong acid is that it breaks up or ionizes 100%. Which means it never goes backwards. The definition of a weak acid is that it breaks up partially. It doesn't break up 100%, but it does break up somewhat. So the Ka was a reflection of, to the extent that it actually breaks up. When you're dealing with Kas, say you have the Ka of acetic acid. Ka of acetic acid is 1.8 times 10 to the negative fifth. You then have what's called the pKa, which was the negative log of the Ka. So if you did the negative log of 1.8 times 10 to the negative fifth, you got a pKa value of 4.74. As far as organic chemists, you find that most organic chemists don't like math. So they like smaller numbers. They just don't, unless they're dealing with physical chemistry along with the organic, they like the numbers as simple as possible. So both of these can represent the acid strength. You'll find in pretty much 95% of your organic resources, when they refer to acid or bases, you're going to focus on the pKa. The reason why is it's just a simpler number. Both these values, the Ka or the pKa, will give you some indication as the strength, the relative strength of an acid. Again, pKa is just smaller values are easier to work with. So if you're given two acids, say you're given acid A, and say you're given acid B, and you're told that the pKa of acid A is 10.7, and you're told that the pKa of acid B is, say, 5.6. You're not going to be expected to calculate Kas or pKa or do any of those ice charts, the equilibrium charts you had to inject them to. You just have to be able to look at this and identify what the relative strength is comparatively. So if I had two acids in front of me and I knew what their pKa values are, the lower the pKa, the stronger the acid. So out of these two, if I just select which one was stronger, I'd say that the second acid is stronger, solely because it's got the lower pKa value. So what we're going to do is, it applies more to when you get into later chapters, when you start getting into more sophisticated reaction. You have multiple areas that can be attacked. They'll refer to the different pKa values and talk about why a certain area of the molecule will be getting attacked over another area of the molecule. The idea that you're supposed to be able to look at and identify is, when they say pKa, they're just trying to tell you, this is the lower pKa value, this is the more acidic component, or region of the molecule. The reason why you got to know that, when you've got a structure, when you've got an organic structure, don't write this down. It's just, find something like this. I got H's all around the structure. 1, 2, 3, 4, 5. You got over 10 H's on a structure alone. An acid is something that's going to donate a hydrogen. So you've got multiple hydrogens within a structure. The idea is taking these pKa values and learning about how different regions of the molecules work based on those pKa values. All those hydrogens could theoretically act as acids and be released from the molecule. If you've got multiple regions, the one that's most acidic is going to be the one that's most likely to act as an acid. So while theoretically any of these H's can be pulled off depending on the type of reagent it reacted with, if I were to throw a really strong base at this, it's going to go after whatever the most acidic component is. So in this particular case, this hydrogen right here will actually be the most acidic on the molecule. I'm not going to go over that now. That's way at the end of organic too. But there are reasons why you got to recognize what's a weak acid and what's a strong acid, because you're going to focus on the most acidic portion of the molecule or the most basic portion of the molecule. A good portion of your organic reactions are acid-base reactions, and again, since these molecules are rather large, you have to know what area to kind of hone in on when you're working on it. But again, that's really more for the later stuff. At this point, it's just giving some general comparisons, recognizing what's stronger. But so given a couple pKa values, you should be able to identify what the stronger acid is out of the two. You don't need to memorize anything in this chart. I don't know why I left that in there. As far as the conjugate, the reason why you have to be able to recognize an acid the acid and the base, and the conjugate acid, the conjugate base. Whatever the strength of an acid or base is, the conjugate is the opposite. So it's literally the conjugate opposite. Whatever the acid turns into is a conjugate base. Whatever the base turns into is a conjugate acid. Whatever strength you started with, you get the opposite. So if you start with something strong, the conjugate is going to be weak. If you start with something that's weak, the conjugate is going to be strong. So if I had a strong acid, so if you looked at this reaction, when you look at a full reaction, the conjugate term is just to indicate what the new stuff is that formed, but technically most of these reactions are reversible, which means that they can go in either direction. So if you were going in this direction, this would be your acid. If you're going in that direction, then this would be your acid. That's the whole point of identifying the acid and the base on the side. Going in this direction, this would be your acid. Going in that direction, this would be your acid. So say you were told some information. Say you were told that this acid had a pKa, let's say 10.7. And say you were told that this acid had a pKa 4.74. And then I asked you, which of those two acids in that reaction is stronger? And the answer should be that the one on the right is stronger. And if I ask you, why is the acid on the right stronger? The answer is that it's at the lower pKa value. So now say I went one step further on that. Say now I asked you, which of the following is stronger? Which of the components in this reaction is a stronger base within the reaction? So I didn't give you any information about pKb values, and I'm not going to give you any information about pKb values or Kb values. When you start jumping back and forth, the trends flip, and it just gets really confusing. You're better off doing it this way than memorizing different numbers. But I gave you information about the acid. I didn't necessarily give you any information about the base, but if you know what I just mentioned, then you do have enough info in front of you. The conjugate is always going to be the opposite strength of what it came from. So if this, out of these two acids, which one of them is a stronger acid? Well, this is the stronger acid. And again, when I say strong or weak, I'm talking comparatively. Comparing both these acids, that one is stronger out of the pair. The reason why it's stronger is because it's got a pKa of 4.74, so I can lower the two values. This right here would therefore be weaker of the two acids. So with that said, in this reaction, which of the bases is weaker? The one on the left or the one on the right? The one on the left. The difference in strength between the conjugate and what it originated from is the exact opposite. If one is strong, the other is weak. If one is weak, the other is strong. So if this base produced this conjugate acid, that means that this is the weaker base. And if this acid produced this base, then that's the weaker acid, and this would be the stronger of the two bases. Now, with the reaction in front of you, another way you could have told which was the weaker or which was the stronger. The strongs always reside on the same side, and the weaks always reside on the same side. You're never going to have the stronger of the two acids with the weaker of the two bases. Once you know what side has something stronger, then that side has to entirely have everything stronger. So another way I could have done that is without making this designation, I simply could look at the two acids. Erase this for a second. Simply could have looked at the two acids and said, well, out of these two with the pKa, this says the lower pKa, that's got the stronger acid. Once I recognize that, everything on that side has to be the stronger of the pairs. And if I know that that's the weaker side, everything on the side has to be the weaker of the pairs. You'll never have one weak and one strong on either side. So as far as this, once I recognize this is a stronger acid, well, this whole side has to be the stronger side. So that means that this is automatically the stronger of the two bases. And once I recognize that as a weak acid, then that whole side has to be the weaker components, which makes that the weaker of the bases. This basically encompasses what you need to be aware of as far as reactions to comparative strengths. Say you had this reaction, I asked you, label the acids, label the bases, identify which ones are strong, identify which ones are weak comparatively, and then once all that's done, identify what is the primary direction that the equilibrium is going to shift towards. So, as far as these go, if I were to label these just to kind of make some sense of this, since you guys don't know the names of these yet, say this was A, say this was B, say this was C, and say this was D. Which of those components are your acids? Now, A is one of them. The definition of an acid is something that loses a hydrogen. So, going from left to right, what lost a hydrogen? Compound A. You had a hydrogen here, and now you don't have a hydrogen here. So this is an acid. Going the opposite direction, going from right to left, what lost a hydrogen?
D.
The H3O+. You went from H3 to H2. Going in this direction, H3 lost. So this is also an acid. If I want to identify the bases, you look, see what's gaining the H in each direction. Going from left to right, what gained a hydrogen? The water. The water went from H2 to H3. You just had to have gained an H. Plus, you're not going to have two acids on the same side. You're not going to have two bases on the same side. Once you know what the acid is on any particular side, the base would be whatever is left over. Once you know the base on any particular side, the acid will be left over. But keeping it in terms of theory, that went from H2 to H3. This gained an H. This would have to be a base. And going from right to left, this was an O negative, and it turned into an OH. This gained a hydrogen going that direction, so this would also be a base. Again, you have one acid, you have one base on each side. You're not going to have two acids on any side, you're not going to have two bases on any side. So that takes care of the first and the second problems. If you want to identify what was stronger, I'm going to show you how you do that without values in just a second, but for right now, you need values. So say I said that the pK here is 4.74, and say I said that the pK here is 1. Which of those is the stronger acid? I don't remember what the acid is. Which of those is the stronger acid?
H3.
H3 plus, whatever is the lowest pKa. So this would be the stronger acid. Comparatively, which means that comparatively, this would be the weaker acid. So as far as the bases, what's the strongest base in that reaction?
CH3 negative.
Right, this compound. If this were the weaker acid, it's going to generate the stronger base. The conjugate is always the opposite strength. The alternative way of looking at it is once you know which side is strong, everything is strong, and once you know what side is weak, everything is weak. But the theory is that the conjugate is the opposite. But shortcut, whatever is the strong side is the strong side, whatever is the weak side is the weak side. So weaker acid generates a stronger base. The stronger acid generates the weaker base. And then the last step is if you want to, this comes up every now and then, if you want to identify what the direction is of the equilibrium, or the primary direction of the equilibrium, you're always going to go from the strong side to the weak side. And that's why it's important that the strong side is entirely strong and the weak side is entirely weak. The equilibrium always goes from strong to weak. So if you were trying to identify what is the primary shift or direction of this equilibrium, in this particular case, it should be going to the left. It should be going towards the reactant side. It should always be flowing from the strong side to the weak side. So that's what this slide is telling you. And that's what this slide is telling me. I probably should have just used the slide instead of writing this whole thing out, but I didn't realize it's still here. Okay, so now that's the first thing I do with acid and bases. If you had a pKa value, comparatively identify which of them is stronger, which of them is weaker. If you had the conjugate bases, identify which of them is stronger, which of them is weaker. If you had a reaction, you'll be able to identify what direction the equilibrium is shifting towards. There's a couple of each of these on the online homework, so if you've gone through that already, you should have seen these. As far as the online homework, 9 of you haven't signed up yet, or as far as a couple days ago, 9 of you haven't signed up yet, so I would try to get that moving if you haven't signed up yet. I sent you a personal email, so if you haven't checked your email box, check it. Please hit sign up for that. But there were several of these on there. That's exactly what you had to do on that is exactly what it is here is exactly what you need to be aware of. Now say you didn't have a pKa value in front of you. Say you weren't told that this is 4 and this is 10. There are ways to identify what the stronger of the two acids happens to be without that. So as far as the exam, you'll have a couple of questions. Some will have one with pKa, one without a pKa, one with a reaction. They're going to be very similar to what I'm doing on the board, conceptually wise. But say you didn't have a pKa value, you wanted to identify what the stronger of the acids happen to be. There's 4. There's 4 main trends that you're looking at. I'm going to go through these a little bit. You don't have to know a ton about them. I'm not going to get nearly as in depth as you need to be on it. It's just more for comparative purpose. So the 4 main rules are, there's the elemental effect, there's an inductive effect, there's resonance, and there's hybridization. Those are the 4 things that will generally affect the acidity of a proton within a molecule. So this slide right here and this slide right here are representing the elemental, that first trend. And then this is kind of putting it all together. As far as the elemental trend, the way to tell which of the following is stronger acids is in general periodic trend. The elemental effect increases to the right and down. The way you can tell that you're dealing with the elemental effect, this particular rule really applies more to general chemistry when you're doing the inorganic acids. It's really not entirely applicable to the organic stuff. The way you can tell you're dealing with elemental, the whole idea of acidity is being able to release a proton or a hydrogen. If that hydrogen is attached directly to different elements, that's when the elemental rule would come in. So say you had HBr versus HI. Looking at these, the hydrogen is directly connected to a bromine, the hydrogen is directly connected to an iodine, the hydrogens are directly connected to completely different elements. If I had something like H2S versus H3P, or let's say H2O versus H3N. Same thing. If I were to look at this, the hydrogens are directly attached to the oxygen. The hydrogens here are directly attached to the nitrogen. The hydrogens are directly attached to different elements. That's what the elemental effect would be considered. The general trend is that the acidity is going to increase as you go to the right and as you go down on the periodic table. There's 2 general things you're looking at when the elemental effect is being applied. You're looking at electronegativity differences and you're looking at size differences of the atoms. As you go across horizontally on a periodic table, the electronegativity changes a lot more than the size of the atom. The reason why electronegativity is a factor, if something is really electronegative, it can pull the electrons harder and more stronger away from that hydrogen. The more you can pull the electrons away, the more easily that hydrogen can fall off. The more easily that can fall off, the more acidic your structure is. Electronegativity does get taken into consideration. The size of the atom also is taken into consideration. If you looked at something like hydrofluoric acid versus, say, hydroiodic acid, when you go vertically on the periodic table, the size of the atom changes more significantly than the electronegativity of the atom. Now, when you have such a huge disparity between, say, a fluorine and an iodine, if you look at HI, that hydrogen is already just inherently kind of separated. It's just so far away from that iodine, it's already practically off of the molecule. When it's in HF, that hydrogen and that fluorine are right on top of each other. It's a much more tightly held hydrogen or bond that you have to overcome in order to break. So, depending on what the trend difference is, what the majority difference is, that's what you're looking at. So in both of these, across the periodic table, horizontal, vertical, what you're comparing is the difference in electronegativity and the difference in the size. So as far as vertical, even though the lower on the periodic table you go, the lower the electronegativity, because the size of the atom increases so rapidly, it kind of overtakes the trend of the acidity. So this is kind of its own thing. If it's an elemental effect, the trend is that the acidity is going to increase as you go to the right, so that's based on electronegativity, and downward, that's based off the size of the atom. So if you have two elements that are on the horizontal, you can just see which one is furthest to the right, that's the more acidic. And if you have two elements that are on the vertical, which one is further down, that's the more acidic. I'm not going to give you something where there's a diagonal, because if there's a diagonal, then you have to have some quantitative data to see does the electronegativity have a bigger difference, or does the size of the atom have a bigger difference, and it just gets too complicated at that point. So if you have two acids and the hydrogens are attached to different types of elements, it's an elemental effect. Your trend is that the acidity is going to increase as you go to the right and as you go down on the periodic table. So if you look at the location of these particular atoms that I selected, if you look at bromine, you've got bromine, you've got iodine, you've got nitrogen, and you've got oxygen. So if you were to look at these comparatively, if I'm looking at each of these sets of acids, I'm trying to identify which of them is stronger, how to pair. As far as HBr and HI, this is an elemental difference because the H's are directly attached to different elements. The trend there is that your acidity increases as you go to the right and down on the periodic table. So I'm going to look at the location of each of these two elements, look at the bromine and iodine, and this increases as you move down on the periodic table. Iodine is a larger atom and therefore more acidic than the bromine. So HI would be more acidic than HBr. Most people are fine with that one because they look at the trend, they look at the periodic table condition, and they see which one goes further down on the vertical, and that's the one that's going to be more acidic. It's the horizontal that tends to get people messed up. And if you take a quick look at this, without going over any of those rules, when I say what's more acidic, H2O or H3N, a lot of students jump on the H3N because they say, well, it's got more H's, so it's got to be more acidic. There's absolutely nothing to do with it. You're losing one H at a time in your games of an acid. It doesn't matter how many you have, can you lose the H easily or not. So when you're looking at these, in this case, the hydrogen is attached to oxygen, the hydrogen is attached to nitrogen. They are attached to different types of elements, and we'll look at those general conditions, and that increases as you go. The horizontal effect increases as you go to the right on the periodic table. So in this case, oxygen is more acidic than a nitrogen. So H2O will be the more acidic out of the pair. It's not based on the number of hydrogens that are attached to the molecule, the element in question. It's where its relative position is on the periodic table. So if the hydrogen is attached to different types of elements, again, the trend is elemental, it's going to increase as you go to the right and down in the periodic table. That, again, is more for the inorganic types of acids. As far as inductive, this is really one of the primary ones that you're going to be dealing with as far as organic chemistry goes. What the inductive effect is, in terms of, when we're going over resonance, and you were actually showing like the arrows with the electrons moving, There's a difference between electrons physically moving from one location to another, and there's a difference between them exerting their influence towards an area without actually moving. So what an inductive effect is when you have an influence over the poles and over the movement of electrons without actually moving them, for the most part. So what this is, in an inductive situation, I'm going to do that over here just because there's a few different examples. As far as the inductive effect is if you have something highly electronegative close to a hydrogen, it may not be able to actually, it itself may not physically be able to pull the electrons, but it can influence the electrons away from the hydrogen. So if I had two structures, now this is what an organic acid looks like. This is referred to as a carboxylic acid functional group. It's on the functional group page handout that I emailed you. I'm going to talk about them briefly tonight. But that's the main functional group, or the main group you're going to see when you talk about acids in organic chemistry. Now, if I had this structure, and separately I had actually, you know what, I'm not going to simplify this one for right now. Say this was a CH2. I don't want to get too far ahead. Okay, say you had those two structures, and you're trying to identify which of those following acids is the most acidic. Now, first off, there's two types of questions I could ask you with those in front of you. I could ask you which of the following two acids out of that pair is more acidic than the other. I could also, given one of those structures, ask you what hydrogen within those structures is the most acidic. So as far as this first compound, out of these hydrogens, you got 1, 2, 3, 4, 5, 6 hydrogens. So let's label those out. So you got, there we go, 1, 2, 3, 4, 5, and 6. Out of those hydrogens, which of those hydrogens is the most acidic? It's going to be number 6. Why? Electronegativity. It has to do with the elemental effect. These hydrogens are attached to carbons, and this hydrogen is attached to an oxygen. That's where an elemental effect can come in. So if you have hydrogen attached to different elements, if I look at the periodic table, I've got carbon and I've got oxygen. So when you have hydrogens that are attached to different elements, your acidity increases as you go further to the right, where you get the more electronegative ones. So within this structure, when I talk about how acidic it is, I'm referring specifically to that hydrogen right there. You hone in, you're going to have multiple hydrogens within these structures, because inherently they're organic molecules that carry hydrogens. When they talk about the acidity of an organic molecule, they're focusing on the most acidic hydrogen within the structure. So likewise, as far as this one, what's the most acidic hydrogen got? Same thing. The one that's attached to the most electronegative element possible. Notice I didn't factor in the chlorine yet. Why didn't I factor the chlorine in yet? There's no hydrogens directly attached to it. I have hydrogen attached to carbon. I have hydrogen attached to carbon. I have hydrogen attached to an oxygen. The one attached to the oxygen is typically the most electronegative, the most acidic one. So that's going to be the one that you're going to focus on. So now that I know what I'm focusing on, that's the first thing I do, is given one of these structures, what's the most acidic proton on it? Again, it's one attached to the oxygen to the elemental effect. Now, comparing both these, if I ask you which of these two structures is the most acidic, I can't really make a determination based, because this hydrogen is attached to what? An oxygen. And this hydrogen is attached to what? An oxygen. So I can't use the elemental. Within the structure, I was able to use that elemental rule to identify that that's the most acidic proton out of the comparison of the rest of them. Yeah. What? Yeah, you're going, yes. So as far as the elemental rule, I can use it within a structure, again, identify that that's the most acidic proton out of the 6 that are in here. When I want to compare these two, I'm looking at the most acidic one here, which is attached to an oxygen, and I'm looking at the most acidic one here, which is also attached to an oxygen. At this point, the elemental rule is not going to determine which of these is the most acidic out of the pair. So what you're then going to look for is what's referred to as an inductive effect. If you have a highly electronegative element in a close proximity to the hydrogen that you're trying to kick away, it may not have a direct grab at these electrons. It can help influence the electrons, even by a small amount. It can help influence those electrons a little closer to itself. Any electrons in its general proximity are going to be pulled towards that chlorine. That's what's referred to as the inductive effect. The inductive effect is when you have an influence over the electrons without actually physically being able to grab that particular pair of electrons and shift them into a different position on the molecule. So while this chlorine may not be directly attached to those electrons, it absolutely has some influence in terms of keep pulling them away from that H. And even by a small amount, the more you can pull those electrons away from the hydrogen, the more acidic the molecule becomes. So in this particular case, what you're looking at is quantity. Which of these two structures has more electronegative elements close to the acidic proton? In this case, it's the structure on the right. This one has one electronegative element attached to it, where this does not have any. This is just kind of bare, it's vacant, there's nothing hydrogens. So if something has one highly electronegative element versus none, it's going to be more acidic. If something has two versus one, whichever has the most electronegative elements close to the hydrogen you're trying to take off is going to be the most acidic compound. Now, you could also get a couple other combinations. You might see something where they both have electronegative elements. So say you had a situation where one structure had chlorine and one structure had a bromine. And you're trying to identify which of these balanced two acids is the most acidic. Well, as far as the inductive effect is, since you're not physically interacting with those electrons, you're just influencing it, the only influence you have over it is through electronegativity. So the trend for the inductive effect is based solely on electronegativity, meaning you increase the right and up. Whatever the most electronegative element is, that's going to have the greatest impact on inductively pulling those electrons away from the hydrogen you're trying to kick off. So if you've got something where, and again, I'm not going to cross scenarios. So you have a situation where something has one electronegative element, one has none. So one is more than the other. The more electronegative elements you have, the more of an impact you have, the more acidic it ends up being. If you have a situation where they have an equal amount of electronegative elements, that has one, but there are different types of electronegative elements. Well, whichever one is more electronegative, it's going to have a greater pull or influence, or inductively be able to pull those electrons away from that proton. So looking at these two, since this is based solely on electronegativity, if I look at the position of chlorine and bromine, chlorine is on top of bromine, electronegativity increases as you go upward. Chlorine is more electronegative than bromine. Since this is based solely on electronegativity, chlorine is going to have a greater inductive pull or inductive effect on those electrons, and therefore it's going to create a more acidic acid out of it too. Like I said, quantity can make a difference. If one has more electronegative elements than something else, the one with more electronegative elements will have a greater cumulative effect in terms of inductance. So the one with two electronegative elements will be greater than one. I'm not going to give you a situation where I give you 2 weaks and 1 strong. And general idea is there's a minor electronegativity difference between bromine and chlorine and iodine. Quantity well outweighs anything else. I'm going to try to avoid doing something like that. But generally, if you have more of something, if I have 2 of any electronegative element, it's going to outweigh 1 of any electronegative element. But if I've got 2 versus 1, the 1 with 2 is going to be more acidic. And the other thing you would be taking into consideration is proximity. Say you had a chlorine on one of them and you had chlorine on another one. generally speaking, the electronegative element should be within a 4-atom span of the hydrant that you're trying to pull off. And I'm not going to quiz you on that, but the reason why I mention that is the closer you are to the hydrant in question, the more of an impact you're going to have. The further it pulls away, it's like 2 magnets. I got 2 magnets with opposite poles facing each other. If they're too far apart, they're not going to connect. If you move closer together, they will connect. So proximity to the hydrant in question. If you look at it, in this particular case, this chlorine is closer to the hydrant you're trying to pull off than this one. That's the only difference between them. They're both the same element, same electronegativities, got the same quantity, they both have 1. This one is actually closer. If you're closer to the hydrant in question, it's going to be more acidic. The closer you are, the greater impact you have on induction those electrons away. That's what the inductive effect is. And this is primarily one of the primary ones you're going to be seeing in organic chemistry. Something as a halogen is usually going to be more acidic than something without a halogen. Yeah.
What if in that first scenario there's no oxygen? Would they all be equally as electronegative?
They would all be equal, yeah. In which case, in that case, you wouldn't be able to say that any of them were more acidic than the other. But then, if that was, say this is a carbon, and say this is a carbon, the one with the halogen, neither one is really acidic, but this one would be more acidic comparatively than the other one, simply because it's got the electronegative element. Resonance is the other one that you're going to end up seeing pop up as far as this book. The reason why resonance really doesn't come too much into play is because resonance occurs when you have a carboxylic acid, and pretty much every acid you're going to work with in this course is going to be carboxylic acid. So there's a reason why carboxylic acids are more acidic than, say, an alcohol. If you were to look at carboxylic acid, but again, this rule, it explains why your carboxylic acids are acid and why alcohol are not, but this one comparatively doesn't come up a whole lot. But if you were to look at a carboxylic acid, and separately you were to look at an alcohol, the way the resonance rule works is something that has more resonance is going to be more acidic. And the reason why is because once that hydrogen leaves, when the hydrogen leaves, it doesn't just fall to the hydrogen, it falls off as an H+. So when that H+ falls off, whatever's left behind becomes negative. Now, negative charge is a charge. Any type of charge is an instability. Resonance helps chop that charge up, distribute it around, and make it less unstable. So it helps to increase the life of that intermediate. It's a better product that results when the H falls off. So what you're going to do is you look at the compounds you got, and you look at what hydrogen fall off and see what it looks like once the hydrogen falls off. So in both these, the hydrogen in question again is one attached to the oxygen. That's one attached to the most electronegative element you got. So if I took this H away, what would be left behind would be a negative charge on the oxygen. And if I took this H away, what will be left behind is a negative on that oxygen. So these are the conjugate bases of those acids. These are what you would get once you behave as an acid, or at least that hydrogen. So what you're going to do now is you're going to take a look and see, well, can I get resonance? Because I can get resonance once it turns into this, that's a good thing. That means that you're stabilizing it, and stabilizing the result, and that means it's a better reaction and you get a better acid. So looking at this second one, when that H falls away and that oxygen becomes negative, that oxygen stays 100% negative. This negative doesn't move. In order to have resonance, you're looking for that 3-atom span, where you got a positive in a double bond, or you got a negative in a double bond. So if you got the negative charge, you don't have any local bonds, you have the positive charge, spontaneous resonance. This is stuck here. That stays exactly as it is. When you look at this does have resonance. Within a 3-atom span, you have a double bond, and you've got a negative charge. You absolutely do have resonance in this situation. Which means that when it undergoes resonance, you're going to end up getting what is essentially 1/2 of a negative charge here, and you're going to get essentially what's 1/2 of a negative charge down here once you actually look at the contributors. And you don't got to draw the contributors out, it's just being able to recognize that it happens. So this undergoes resonance, which means that it can chop that negative apart, which means it can make it more stable. If the result that you get after the H falls off is more stable, then it falls off easily. Reactions happen to form something that's generally more stable. They try not to form something that's less stable. It's just not thermodynamically favorable. So if I can split this up to resonance, that's great. I mean, the H will fall off, what the results will be stabilized, and everything's happy. If the H falls off, and what's left over does not get resonance stabilized, and it's just not as stable and doesn't work as well. So if the conjugate base of an acid results in resonance where something else doesn't, or something has more resonance, because it's going to get 3 contributors versus 2 contributors, the more resonance you have after the H falls off, the more acidic the compound ends up being. So out of these two, I would say that since this one has resonance on the top and the bottom one does not have resonance, the one with resonance would end up being the more stable one. Which is why what I had drawn here was an alcohol, and what I had drawn here was the carboxylic acid. The reason why these are called your acids for organic chemistry are called acids because they're most likely to behave as acids. The reason why they're more likely to behave as acids is because they're resonance stabilized. So inherently that rule comes along through organic. You don't really focus on it too much. All your acids are carboxylic acids because of that resonance stabilization. But this explains why a carboxylic acid is more acidic than an alcohol. This one is resonance and this one is not. And hybridization is the least used of the rule. This states very simply is that a hydrogen attached to an sp1 is going to be more acidic than a hydrogen that's attached to an sp2, which is more acidic than a hydrogen that's attached to an sp3. So what that means, if I were to look at this structure, this structure, and this structure. If I have those 3 compounds in front of me, and I wanted to identify between those 3, what is the strongest acid out of those? If you notice, hybridization is the last one on this list. The reason why it's the last one on this list is because it has the least impact in terms of the acidity. Now, I can't use the elemental effect. The reason why I can't use the elemental effect is because in all 3 of the structures, your H's are attached to carbon. There's no difference in the element that the H's are attached to. You can't use the elemental effect. So I go to rule number 2. I can't use the inductive effect, because using the inductive effect, I'd have to have something electronegative, meaning like an oxygen or a nitrogen or a halogen. And all 3 of those lack oxygens and nitrogens and halogens. They all lack electronegative elements, therefore none of them exhibit the inductive effect. None of them are going to exhibit resonance, just because you don't have any scenarios that would exhibit resonance. These are all 2-carbon strings. You need a 3-carbon string in order to get resonance. Literally the only thing that can be applied is what is the hybridization of the atom that the hydrogen happens to be attached to. It's the only thing you can look at. So if you were to look at the top structure, what's the hybridization of the carbon that the H's are attached to?
SP3.
This is sp3. And if you looked at this structure, what is the hybridization of the carbon that the H's are attached to?
SP2.
This is sp2. And if you look here, the hybridization of the carbon that the H's are attached to here are sp1. So out of these 3 structures, it's the only rule we got left. Out of these 3 structures, which of those has the most acidic protons? The bottom one. Hydrogens attached to something that's sp1 will be more acidic than things that are attached to sp2, which are more acidic than things that are attached to sp3. Which is why, as far as structures that contain nothing but carbon and hydrogen, these are called alkenes, which I'm going to get to in a little bit. Alkenes, you go through the entire chapter, they're never going to reference the acidity of an alkane. The reason why, there's nothing about them that makes them acidic. When it's alkenes, which is where you have the double bond, they are not going to mention anything about acidity. The same thing, there's nothing on here that would make this even relatively acidic, even in the presence of a really strong base. Now when you get to the alkyne, you have the triple bond, you're finally getting to a point where these hydrogens are just barely acidic enough to react with one of the strongest bases out there. But this is finally entering into a state where this can actually lose a hydrogen. So you're not going to see any reactions, for the most part, where they're going to pull H's off of an alkane and say, hey, this is an acid. You're not going to see it with alkenes either. You're not going to see it until chapter 9. So when you get to chapter 9, it's kind of an offshoot reaction, and it's way into the semester. I'll bring this up again as to why we're focusing on it. But hybridization, it's a very minor impact, but it does have somewhat of an impact on the hydrogens. So you would only use that rule if there's nothing else to look at. But again, the 2 main ones you'll generally see come up are the elemental and the inductive. Those are the 2 you'll see referenced the most. The 2 that will consistently come up with the reactions are inductive and resonance. Again, resonance, you're typically not going to have a whole lot to compare it to because every acid that you're going to be working with in organic has resonance. Which means that really the main one that you're working off of is inductive. The one that I can come up with the most types of questions on would be an inductive effect. Yeah.
I know on the homework there were some questions where it would have like multiple chlorine in the same bond, but you're also comparing the bromine versus the chlorine. I just want to know like what.
The quantity makes a difference. Whatever is the most is the first thing to look at.
Okay.
And only if you get the same number, then you look at what's stronger or how close is it. But the quantity absolutely outweighs anything else.
Okay. Thank you.
Alright, so those are the four main things you're looking for as far as acidity. The homework problems are pretty standard as far as what you'd be seeing. Again, the questions in front of the board are pretty much what you'd be seeing. Most of the ways that they're going to be asked is give you a couple pairs of acids, simply say circle which one is stronger. But again, first look to see if the H is attached to different elements. That's the elemental effect. If that can't be used, then you look to see if there's just electronegative elements in the region. That's the inductive effect. And if that can't be used, it's one of the remaining two. It's pretty easy to identify the hybridization because that's the only time you're going to see single bond and double bond and triple bonds kind of floating around because that's what changes the hybridization. But that's what all those slides are dealing with. As far as the Lewis acid and Lewis bases, again, I'm not going to touch on that for right now. Lewis bases are called nucleophiles. Lewis acids are called electrophiles. When we get to the chapter that's relevant to it, I'm going to come back to it. I'm not going to go over that. I don't want to teach something under one term and then teach two. Yeah, just for some reason, I'll teach Lewis acid, Lewis bases, then I'll come back into it 2 chapters later and say, well, this is a nucleophile, this is an electrophile, and the connection is just never made. So I'd rather hold off on this till we're actually discussing nucleophiles and actually discussing electrophiles. It'll come across better that way. All right, so the last part of this chapter, and then I'll give you a break. The last part of this chapter is dealing with functional groups. Now, I'm going to run through a couple slides. This really, for the most part, is memorization. So I'm going to show you what this is dealing with. As far as the types of functional groups that you're going to have to be aware of. The purpose of identifying functional groups is they're essentially your reactive points. Where is the reaction most likely to occur in structure? And I mentioned at the beginning of the semester that polar bonds create a reactive point and pi bonds create a reactive point. So what all the functional groups are doing is saying, well, these are the reactive points. And you'll notice that they all contain pi bonds, or they all contain oxygen, or they all contain nitrogen, they all contain a polar bond or a pi bond. So the functional groups are just kind of honing in on the reactive regions within a molecule. If you have nothing but carbon and hydrogen, meaning no oxygens, no nitrogens, no halogens, no nothing, just carbon and hydrogen, those are referred to as hydrocarbons. Hydro for hydrogen, carbon for carbon, hydrocarbons. So a hydrocarbon is something that contains nothing but carbon and hydrogen. This would be an example of hydrocarbon, this would be an example of hydrocarbon, and this would be an example of hydrocarbon. They all contain nothing but carbon and hydrogens. They start throwing oxygens into it, and nitrogens, and halogens, or whatever else are thrown into it. It's no longer classified as hydrocarbon, and it'll then be classified as something else. So hydrocarbons are just carbon and hydrogen. That's one type of functional. There's going to be one broad class of functional groups. There are ones that contain oxygen, and there are ones that contain nitrogen. So as far as the ones that are just carbon and just hydrogen, the three you've got to be familiar with: alkanes, alkenes, and alkynes. The way you're going to recognize it: alkanes, there's all single bonds. Nothing but single bonds within the structure. An alkene has at least one carbon-carbon double bond. So make that designation. For alkenes, saying double bonds are present. A double bond between a carbon and an oxygen is not an alkene. So it's not just any double bond. An alkene is specifically when you have at least one double bond between 2 carbons. So a carbon-carbon double bond specifically. It's not just any double bond. If you have 1 of them, if you have 2 of them, if you have 3 of them, it's an alkene. The presence of a single carbon-carbon double bond is classified as an alkene. An alkyne would be at least 1 carbon-carbon triple bond. So if you have a carbon-carbon triple bond, that would be an alkyne. So now looking at these, this had a carbon-carbon triple bond, so this would be classified as an alkyne. This had a carbon-carbon double bond, that would be classified as an alkene. And this had all carbon-carbon single bonds, that would be classified as an alkene. So if you have at least 1 double bond, it's an alkene. If you have at least 1 triple bond, it's an alkyne. You don't have to have all double bonds and all triple bonds. If I had something like this, I have a structure like that. Well, I've got carbon-carbon single bond, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon single, carbon-carbon single, carbon-carbon single. If you have at least one double bond between the carbons, the entire thing is classified as an alkene. If you have at least one triple bond, the entire thing is classified as an alkyne. If you have literally no double bonds between your carbons and no triple bonds between your carbons, at that point it's classified as an alkene. Alright, so those three, a cyclo structure simply means it's a ring. I'm not going to ask you to separately identify that, but cyclo means a ring structure. So there's a difference between drawing 1, 2, 3, 4, 5 carbons straight and drawing 1, 2, 3, 4, 5 carbons in a ring. Alright, this would be an alkane. Because it's got all single bonds between the carbons. And this would be a cycloalkane. It's an alkane because it's got all single bonds between your carbons. It's cyclo because it's in a ring shape, which means it's continuously connected. An aromatic means that it contains a benzene ring. So for an aromatic structure, they're pretty easy to identify. If you see this structure, this is what's referred to as benzene. It's one of many aromatic compounds. At this point, as far as you're concerned, it's the only aromatic compound. So if you see this structure, this is classified as an aromatic functional group. If you classify it as a benzene on the exam, I'm fine with that. But in general, it's an aromatic functional group. It's benzene. It's the only one that you're going to be dealing with in this semester. If you take organic 2, you'll see that there's numerous organic aromatic molecules out there. And it'll go over the rules at that point, how you identify them. But those are the basic ones. Those are your hydrocarbons. You have alkenes, where it's all carbon-carbon single bonds. You have alkenes, where it's at least one carbon-carbon double bond. And you have an alkyne, where it's at least one carbon-carbon triple bond. Then you get into your oxygen and your nitrogen ones. So what I'm going to do, I'm going to pull up the handout that I gave to you in order to explain the rest of these. I'm not going to go through these slides as far as, you can look through these on your own as far as what analysis is. I'm not going to ask you to memorize all these either. Like for example, carboxylic acid derivatives, we're not going to be going over acid chlorides, we're not going to be going over nitriles. So these were here just more to for you to have a resource. The ones that I want you to be familiar with are the ones that were on that handout. So the handout that I sent looks like this. Okay, so this was a handout that I emailed you. These are, aside from the hydrocarbon, aside from identifying an alkene, an alkene, and an alkyne, these are the main functional groups I want you to be able to recognize. These are the ones that I'll be asking on the exam. There were other ones in those slides that I'm not going to, this is what I want you to be familiar with. So the way the problems are going to go, but for the most part, really at this point, it's going to be memorization. We're not going to deal with most of these functional groups this semester. The only way you will deal with them is if we're working if you take organic 2 and we actually get to those particular chapters. But this semester primarily deals with the hydrocarbons, the alkanes, the alkenes, and the alkynes. Next semester deals with the oxygen and the nitrogen-containing functional groups. The way a problem like this is going to be posed is, given a structure, be able to identify the functional groups that are in it. I generally pick some type of a pharmaceutical compound that has like 5 or 6 functional groups, and I ask you to circle them and identify them. So being able to identify an alcohol, being able to identify an aldehyde, being able to identify a ketone. When you look at these functional groups, if you look at the aldehyde and the ketone and the carboxylic acid and the ester, they all have carbons double bonded to an oxygen. A carbon that's double bonded to an oxygen is known as a carbonyl. So those are referred to as carbonyl-containing functional groups. An aldehyde is a carbonyl-containing functional group. A ketone is a carbonyl-containing functional group. An ester is a carbonyl-containing functional group. The carbonyls are highly reactive points within a molecule. So when you get, if you take organic 2 and you get to the aldehyde chapter and the ketone chapter and the ester chapter, they're solely focused on attacks at that carbonyl structure. The reason why it's such a perfect functional group is the two things that make something reactive are a polar bond or a pi bond. This is both. And it's got a polar bond because you got the partial negative on the oxygen and you have the partial positive on carbon. And it's got a pi bond. It's even got the loosely held electron in between them. So it's got everything about it that makes it reactive. It is one of the most reactive parts of a molecule you can find. So if you come, when you get to a chapter that deals with these functional groups, every reaction is based off attached at that particular location. So you might have a structure that's 100 carbons long. You're solely focusing on that carbonyl region. The rest of it just kind of gets carried along with the reaction. It's not actually meant to take part in the reaction. But say I gave you a structure that looks something like, just to give you an idea of what you might see. Again, you'll get a structure, it generally contains about 4 or 5, maybe 6 functional groups. I ask you to circle and identify what they are. So say you had it's something like this, and I ask you to circle the functional groups that are located in it and identify what they are. Functional groups, again, are just giving a way of giving a name to the reactive points that are in a molecule. And reactive points either have a pi bond or they have a polar bond. You get a pi bond by having a multiple bond, and you get a polar bond by having an oxygen, a nitrogen, or a halogen. So when you look at a structure like this, you should be honing in on those reactive points. So looking at the structure, that's a reactive point. I know it's a reactive point because it's going to be a polar bond. There's an oxygen or nitrogen or halogen. I know that this is going to be a reactive point because it's got a polar bond. It's got an oxygen, a nitrogen, or a halogen. I know that this is going to be a reactive point of a molecule because it's got a polar bond, it's got an oxygen or nitrogen or halogen, plus it's got a pi bond. So those are the 3 reactive points. Again, functional groups are just assigning names to these reactive points or reactive regions along a molecule. So that's why on the right, I gave you that column of what they look like in the line structure. I'm giving you a line angle drawing, probably bigger than this. They're a little bit more separated. It's a little easier to isolate and identify them. But I'll give you a structure like this, and then I say circle the functional groups and identify what they are. So it really, most of this is just memorization and getting used to what they look like. This is really just kind of setting up the flashcards and going through them a couple of times. But if I were going to identify what these are, as far as this one, this is a nitrogen attached to it. So if you look at the sheet, again, these are the only ones you've got to be familiar with. So if you look at these, as far as nitrogen, you've got amines and you've got amides. So the main difference between them, an amine is a nitrogen attached to a carbon, and an amide is a nitrogen directly attached to a carbonyl. So what you're going to do is, we've got a nitrogen, which means it's either an amine or an amide. An amine is when you're attached to a carbon, a regular carbon. Amide is when you're attached to a carbonyl. So looking at this, would this be an amine or would this be an amide?
Amine.
It'd be an amine. You got the nitrogen, but it's not attached to a carbonyl. In order for it to be an amide, the nitrogen has to be directly attached to a carbonyl. And if it's not directly attached to a carbonyl, it's an amine. It's not directly attached to a carbonyl, so it's an amine. All right, if I look at that one in the middle, if I look at that second one, and it's just an oxygen stuck in between 2 carbons. Now, when you look at the shorthand of what I wrote on here, you see those R's that are in those formulas? An R group is any carbon structure. Any carbon structure you can possibly imagine. 1 carbon big, 1,000 carbons big, rings, no rings, multiple bonds. Any carbon structure you can possibly imagine is what the R group is representing. Any carbon structure. So what you're looking for is an oxygen that is stuck directly between 2 carbons. So if you look at the ether is where you have a carbon stuck directly between 2 oxygens. The reason why it's not a ketone or an aldehyde or any of those is because those all contain carbonyls. And one of the major components of a carbonyl is a double bond. You don't have a double bond here. So since you have an oxygen, you don't have a double bond. So the lack of double bond rules are aldehydes, ketones, carboxylic acids, esters, and that basically leaves you with an alcohol or an ether. So in alcohol, the oxygen is attached to a hydrogen. In an ether, the oxygen is not attached to a hydrogen, it's just attached between two carbons. So this particular functional group is going to be an ether. It's a carbon trapped directly between two carbons. It doesn't matter if it's in a ring, it doesn't matter if it's in a straight chain, it's a carbon stuck between, it's an oxygen stuck between two carbons. And for this third one, you've got a carbonyl. So if you've got a carbonyl, that gives you 4 options. You've got aldehyde, ketone, carboxylic acid, and an ester. In the case of carboxylic acid and in the case of an ester, if you look at the carboxylic acid and esters, the carbonyl is directly touching an oxygen. And in this case, your carbonyl is not directly touching an oxygen, which means that it can't be an ester, because an ester, the carbonyl is directly touching an oxygen, and it can't be a carboxylic acid, because in a carboxylic acid, the carbonyl is directly touching an oxygen. So those two are out, which leaves you with the only 2 remaining that are on the sheet that have a carbonyl are your aldehyde and your ketone. Structurally and reactivity-wise, they're almost identical to each other. The only real difference between an aldehyde and a ketone is that a ketone, the carbonyl is in the middle of a structure, it's in between carbons, and an aldehyde is at the end of a structure. So it's at the tail end, which means that it's attached to a hydrogen. So looking at this particular step, is that an aldehyde or is that a ketone?
Aldehyde.
It's an aldehyde because it's a carbonyl that on one side is a carbon, on the other side is a hydrogen. It's a carbonyl at the end of a chain. So this would be classified as an aldehyde. That's exactly the type of problem that you expect. That's the extent of what you have to be aware of as far as functional groups. The only other way that this would be presented would, if you look at the condensed column, I do want you to, if you're giving them a formula, be able to recognize an aldehyde or a ketone or something along those lines. I didn't used to do that. The reason why I started doing that is because the pre-professional exams do that. It's annoying. I don't know. I would prefer that they didn't, but they do. Most of the time when you see these written out, if there's a double bond O, it'll clearly show a double bond O in the structure, unless you're on one of these exams and they're trying to trick you, and then they condense it. So because of that, I gave you a condensed column, so you should be able to recognize an aldehyde from a condensed formula or a ketone from a condensed formula. So if I gave you, for example, if I gave you 2 compounds, if I said you had a CH3, CH2, CHO, and I said you got a CH3, CH2, CH2OH, and I asked you which of the following was an aldehyde. You should be able to look at those 2 structures and based on that condensed formula identify what the aldehyde is. So the aldehyde would be classified by the CHO, whereas an alcohol would be classified by an OH. Carboxylic acid would be a COOH. Be able to recognize them within a structure. So given these 2 formulas, I want to identify the aldehyde, and aldehyde is identified by that CHO at the end of the molecule. If I wanted to classify both these, I'd say this top structure, because this CHO is an aldehyde, and I say that the second formula, because the OH is an alcohol. So I'll be able to look at a condensed formula and identify what the functional group happens to be. If that's worth 1 point, this will be worth about 5 points. I'm predominantly looking for you to be able to identify within a structure of what the functional groups are that are present. Again, the reason why I'm throwing this down there is just because the pre-professional exams do want you to be able to recognize that. So now it's time to do it. But those are the 2 ways to see functional groups. Again, beyond that, I'm not asking about comparative reactivities or anything along those lines. I'm not asking anything. I want you to simply be able to recognize the functional groups in the structure. But that's, like I said, functional groups, make a couple flashcards with these. Be able to recognize them in a line structure, be able to recognize them in a condensed formula. But that's, so there's a lot of slides in chapter 2 on the functional groups. Again, I didn't even really look at toward the extent that they explained them. It's just a recognizing thing that I want you to go through with us right now. All right, so as far as chapter 2, that's chapter 2. Chapter 3, we're going to start off with naming of alkanes. So it's 7:16. I'm going to give you a 10-minute break. 10 minutes, come back to this.